stream there. All right. Okay, so we've got an extra one. That's okay. All right. Let's see, who else we got? Esmeralda's here. Jackie. Here. And Sophia. Still missing Annie and Melissa. And they're not here in person. Oh, I can take this off at least. Well, we'll start there and see where it goes. Anyways, good afternoon, everyone. Our quotation this morning is a reminder to always keep moving, keep making progress, no matter what. And so the progress we're going to make is in the realm of geometry. And so what we're going to do first, as we have been, is open up yesterday's work with the volume and go ahead and compare your answers there to my answers here. And ask away. Now, a few of these turned out to be a little more challenging than maybe you expected. And to be fair, I did warn you to watch out for what information you actually need versus what information they actually give you. Right? And that was the case of the regular hexagons we couldn't quite deal with yet. The right triangular prism, though, we can totally do that. Although it takes a little bit of thinking, because you have to understand that, well, there's no way that that's going to be a right angle. There has to be one somewhere, and this is the only one that makes sense. And I have to bring this 6 over here, and that's the same as that leg there. So the two legs of my right triangle are both 6. That's what I'm going to multiply. The 10 has nothing to do with it. But on number 2, oh, they were so tricksy on number 2. See, once again, I have to bring this 6 down, so I have all my measurements of my trapezoid in one place. But for a trapezoid, I need the 2 bases and the height. And I have my 2 bases, 3 and 6, but they don't tell me the height. I've got to figure that out. And this is where, if you already know the Pythagorean Theorem, which I'm sure many of you do, you could use that here. We will be talking about it explicitly next week. So by then we can definitely come back and finish these up, fully understand them. But just real quick here, if I know this whole base is 6 and this part is 3, then drawing another perpendicular line here. You can draw in any line you want, and you can specify, I want to draw this in so it's perpendicular. Right? That means then this much is also 3. So from 6, that leaves 3 over here. And now I have 2 sides of my right triangle. Pythagorean theorem gives me that the square of the hypotenuse side is equal to the sum of the squares of the other 2 sides. So I can use that to solve for that final side of 4. Now I have the height of my trapezoid. I can find its area and then times 8 to get the volume of the prism. So that one was kind of sneaky. They hid that bit from you. 4, 5, and 6, though, were much more straightforward. The catch being that you are using algebraic expressions. You're not actually filling in final numbers there. And so ideally, you would just fill in as given, treat it exactly as if it was a number, but then try to simplify as much as you can. So the volume here, multiplying those, distribute that, you get these 2 terms. On the cylinder, right, this is the circumference, so you want to work backwards to find the radius. Okay. And this one has the rectangle plus this half a cylinder, and then you can factor out that x squared y. So this is similar to this guy. You could have had this written out as 6x squared y plus 3x squared y pi, or 3 pi x squared y. Those would still be acceptable. And then number 7 was seemingly so simple. It's just a bunch of rectangular prisms. Not too bad. And then, oh wait. I'm sure somebody got tripped up by the units here. These are in inches. This is in feet, and they wanted cubic feet. So you have to convert this. 6 inches is half a foot. Okay? And then multiply and add them all up, and you get 6. Any questions on that page? No? All right, the next page. Some similar challenges. The first pyramid, 80 centimeters cubed. It's square base. They give you the height, no problems there. Number 2 is the hexagon. We talked about that. We'll come back to it next week. 3, this is half of a cone, which wouldn't be too bad in and of itself, except they gave you the slant height, not the actual height. So once again, Pythagorean Theorem to the rescue to find that should have been a 24, and you can solve the rest from there with the cone formula, and then divide by 2. And that same triangle shows up again on number 4. 725 gives 24 because you need the perpendicular. Here's the right angle. You need to multiply the perpendicular ones to get the area of this triangle. And then it's not a triangular prism, it's a triangular triangle. So you need to multiply by half when you get this triangle's area, and then when you multiply by the height, and then take half again. Okay? And this is just 2 cones pushed together. Number 6, however, solid generated by spinning a triangle around the axis. So if you follow their little curvature mark there and you curve everything around, what you end up with is just a cone. So represented as a triangle, but if you were to spin this, and I wish I had a prop I could use to demonstrate this, but if you spin it around, it starts to look like a cone. It fills up the space of a cone. And then finally, 7, 8, 9. The comparisons here. No units were given, so I'm just listing them as units cubed, cubic units. Just a generic measurement there. And you have the cylinder and cone here. This cone is, in fact, bigger than the cylinder. Despite being a cone and having that 1/3 there, the dimensions are large enough. This is much bigger. Number 8, these 2 triangular wedge shapes have all of the exact same dimensions, so they have the exact same volume. Neither is larger. And number 9, who wins 3 small cones or 1 triple-sized cone? The triple size wins. Notice this is a radius of 3 on each of these. So in theory, it should be, well, if it's 3 times bigger, right? 9 is 3 times 3. Shouldn't I have 3 times 3 here? But that's only in one dimension. It's 3 times bigger this way and this way. So that makes a compounded effect. So you end up much bigger volume overall with a single large cone. Okay. Any questions from that page? No? All right, then let's go on. Today we are finishing off surface area and volume with one last shape we've otherwise neglected here, and that is spheres, right? Everybody's favorite space balls. Of course, how do you find the surface area and volume of a sphere? Well, spheres are just 3-dimensional circles. So we should know they're always going to involve that fancy number pi. And they're, of course, going to be based on the radius of the circle in question. except volume is three-dimensional, so it's going to be r cubed. Surface area is still a two-dimensional measurement, so it's only r squared, just like the area of a single flat circle. But there's, of course, much more to it. When you go into that third dimension, the surface area is no longer just a single circle. It's actually turns out to be 4 times that circle. Why it comes out to be 4 times as much is a derivation for another day. But just understand the surface area is 4 times pi r squared. And the volume, similarly, we went out to those 3 dimensions, we still get 4 times as many circles. But just like the cone, you're dealing with a third of the volume at a time, because it kind of chops off all of the corners, as it were, compared to, say, a cylinder. This equation for the volume you will be given. That is included on that SAT formula sheet. So this one you don't need to memorize per se. This one you at least need to recognize the relationship between surface area and volume. Understand that surface area is 1 power less of the radius, because it's 1 dimension less. And it doesn't have this divided by 3, but it still keeps the 4. So if you can recognize that and say, hey, I have this, can I real quick jot down how does that change into the surface area formula, so you have that if it's ever needed. Okay. And then today's questions are going to be much more straightforward, because we don't have to deal with these tricksy triangles and polygons that we haven't gotten to yet. It's all round shapes for today. So first page is all volume of spheres and portions of spheres. If it's a fraction of a sphere, it's just a fraction of that volume. So this guy is half, just like a grapefruit you might eat in the morning. Okay, this guy is taken half of a half. Okay, so that's a quarter left over. Right? Number 4, you're going to have to figure out what fraction of this sphere is left. They've taken out a little wedge slice here out of only the upper half has the chunk missing, but how much of that half is missing? Well, they tell you it's got a 90-degree arc there. So out of the full 360 degrees, how much is not there? I'll leave you to answer that one. 5 is interesting. They only give you the heights here. Can you find the radius? You're going to need the radius. All of these share the same radius, and they depend on that single measure. I have to do a little bit of thinking to figure that one out there. And number 6, watch out that the hemisphere is taken out of the top. Okay, so you're going to be subtracting that from the cylinder there. But otherwise, these are not so tricky. We don't need extra information here. Speaking of extra, since you guys are here, and anybody watching at home, a little extra bonus for you tuning into the video and coming in for class. So Brian, you're getting this one for free. Go ahead and skip 9 and 10. I didn't include that in the Google Classroom directions. I'm putting it here now, so those of you that watched through the whole video, you will know that you get to skip 9 and 10. And if you didn't watch, you're going to be spending extra time on it. They're good questions. They're worth the time. So if you have some extra time, you're like, I'm really bored today after work. You know, what else can I do? Oh, I've got those awesome math questions right here. Okay? But for the sake of time, since it is a double helping today, I'm going to trim those off. Similarly, surface area of spheres, we bring in a few other shapes as well, because just a single sphere is boring. You do that once and it's the same every time. So let's see about different combinations. And again, cross out the final question, number 7 there. You can skip that one for today. Maybe we'll bring them back later, maybe like next semester. We'll do more word problems then. But the catch with the surface area, as with any combined shapes, is please remember that you're not counting the surfaces where they contact. Okay, imagine you had to paint this object. You can't paint the circle here at the base of that cone because it's covered by the hemisphere. Right? Similarly, you have this whole cube that gets every face covered except the top has this circle covered on it. So you do need to include these little corners, but you do not want to count the circle here. You do want to count the dome. Okay? You're going to have to determine what you need to add and subtract in order to arrive at your answer there. Any questions then on today's practice? Okay, hearing none, then I will cut the stream here and leave you to it. Do chime in if you do come up with anything.